Hello, and welcome to Lab 4, which is our acid-base titration lab, and I'm going to be explaining everything from the pre-lab right now. Okay, so the purpose of this experiment is to analyze the percent of the acetic acid by using titration and to determine the molarity and percent of mass. And then now let's go into our properties and safety. So for potassium hydroxide is an odorless white-yellow solid. It is reactive and moisture sensitive and air sensitive. And water we know is colorless, odorless, liquid, and it's stable. Now, one that is difficult for me to say, phenolphthalein indicator is odorless, almost white, solid, and stable under normal temperature and pressures. Then your acetic acid is a vinegar-like, colorless liquid, stable under normal conditions. Now, moving on to our pre-lab questions. So our first question was to explain different terms, so I'll go into that. First is analyte. Analyte is a chemical that is the subject of an analysis. Then the next one, a titrant, is the known concentration being added to another to find the other's concentration. Next is an indicator. An indicator solution is any substance that gives a visible sign of a threshold concentration of a chemical. Now, next is endpoint. An endpoint is the completion of a reaction. Then equivalence point is the color change at the end point. A buffer region is the region where pH remains constant, and pKa is negative log of the acid dissociation constant, which is Ka, and next Ka is the equilibrium constant. A titration curve is the plot of the pH of the analyte versus the volume of the titrant added. Now, moving on to question 2. Is there a difference between your endpoint and equivalence point? There is. The difference between your endpoint and equivalence point is that you need the equivalence point to occur for the endpoint to come after it. So there are different, but one of them is helping you get to another. Now, question 3. What is the normal Ka for the analyte acetic acid? Acetic acid is a weak one. Oh, sorry. Number 3 is identify the strength. That's why I was confusing. So, as I said, acetic acid is a weak acid. And moving on to question 4, which I accidentally stated before, the normal Ka for the acetic acid is 1.8 times 10 to the negative 5th. Then, so for number 5, the pH range for your indicator. The pH range for phenolphthalein indicator is 8.2 to 10. I am so sorry. And then we move on to question 6, which is writing out the balanced equation performed, and you will be able, through the pictures, to be able to see that, the balanced equation shown. Number 7, calculate the volume of 0.125 NaOH needed to neutralize 25 milliliters of 0.1 molarity of HCl. So I'm going to explain a little bit of what I did. So all you do is you multiply 1.25 molarity to your X, is the one that you don't know, equals your 0.1 molarity times 25 milliliters. And of course, that put together, it would be 2.5 divided by 0.125, and at the end, your X will be 20 milliliters. Now, for the last question, what is the concentration of a sulfuric acid solution if 50 milliliters of a 0.25 molarity KOH is needed to neutralize 20 milliliters of H2SO4 solution of an unknown concentration? So, first we balance the equation, which will be shown on the paper. And then what we do is we're multiplying 2 times 20 because there's 2 KOH, so then you multiply that 2 times the 20 milliliters times that X will equal 1 because your H2SO4 is 1. Or sorry, your K2SO4 is only one of them, times your 50 milliliters, then times your 0.25. So then after you do that equation, the molarity at the end of H2SO4 is 0.3125 at the end. And that is your pre-lab, so let's get back into our lab. Hello and welcome to Lab 4, our acid-base titration lab. Here I've already started with setting up everything, setting up the burette to how it's supposed to be, and our base and acid have already been made. So now we're about to start putting in 0.5 milliliters into titrating it into our substance. So let's begin. So I'm just gonna turn it. I'm gonna let it go. It's stuck. Okay. And that is our first. Now let me stir it around for a second. And that is our first titration, and I'll be back whenever I have more results. Okay, so for the first titration, let's test the pH. So I'm just gonna stick that in there. The initial pH that I saw before starting was 3.2, and for adding 0.5 milliliters of KOH, we have it now at 3.3 as our pH. Okay, so back in trial one, I've gotten to where we've put in 4 milliliters of the KOH titrated it into this substance, and the pH after just checking is 3.8 after 4 milliliters is in. But at the beginning, with our initial, whenever it was at 0.0 milliliters been titrated, its pH was at 3.2. So we're seeing our pH go up slightly over time. Okay, so checking back in on trial run, I've titrated at this point 8 milliliters of KOH into our solution. And after 8 milliliters, our pH now is at a 4.1, and of course compared to our initial, which was 3.2, we've made little ways since then, so we'll see what happens in a little bit. Checking back in, we have now titrated 12 milliliters of our KOH into there, and our pH after checking was at the pH of 4.6, so it has gone up slightly since the last 4 milliliters that I checked in with. Okay, so checking back in with our titration, I have gotten it to that I've titrated 16 milliliters, and the pH that was just checked for 60 milliliters came out to be 4.7 pH. So it's still going, but we'll see what happens in a little bit. Okay, so 24 milliliters in, our pH is still at a 5.1, and there doesn't seem to be any signs of it turning pink. It's still that very clear, colorless. It still doesn't have that light pink shade where it would be if it was getting close to or at the equivalence point. Hello, so we have put in 32 milliliters at this point, and it's been slowly going up, and at this point now it's at 5.7 milliliters, but there were starting to be signs that it was, once it was added before the little swirling method that we do in between, that it created this pink color. So from knowing that, we're getting closer and closer to our equivalence point, so that's exciting. So yeah. Okay, so we reached 39 milliliters of our titrant being titrated into our analyte, and our the pH has moved from being in the 5s to being at 6.0, and there's been showing a lot more signs of having this pink show up as it was being titrated. And so we're getting pretty close to the equivalence point. So I'm excited about that. So checking back in super early, our substance stayed the color of pink for relatively close to 30 seconds. And so I believe we're at our equivalence point, and that was at 40 milliliters, and the pH was 6.2 at that time. So we'll get to our end point, and then buffer it, and then move on to our next trial. Okay, so we reached past the equivalence point, because now I will show at 6.9. That's 6.9 pH. So. Okay, so now we're back for trial 2, and I have put up everything, and I have checked its initial milliliters for how much of the titrant is in it, which is 0.0, and its pH at the very start, and that was at 3.5. So I made sure I recalibrated everything just to make sure that there wouldn't be any crazy differences to make sure. So let's start off with our first milliliter, and we'll get going. Okay, so here we go. Now about to titrate 1 milliliter into our, and there we go. Now let me swirl it for a sec, and now let me test its pH, and on camera I'll tell you. Interesting. Okay, so the pH for this says that it is at 3.0 for our start with 1 milliliter. So I'll be back a little bit later as we get closer and closer to our equivalence point and end point. Okay, so 4 milliliters in for trial 2. our pH has turned out to be at 3.4 pH, while our initial for it, I accidentally said it wrong, it was 3.0 for our initial. So we'll be back in a little bit to see how this changes. Okay, so after titrating 11 milliliters of our KOH into our analyte, its pH has moved up to being at 4.0, and it stayed at 4.0 for a little bit so far. So we'll see what happens once we add more of our KOH to it. Okay, so a little bit later check-in, we're now at 20 milliliters have been titrated in, and our pH is now at 4.4, which is a big difference from whenever we started at 3.0. So we'll see what happens the later we go. Okay, so we're at 30 milliliters in, that has been titrated in, and we're starting to see, it was relatively around 27 milliliters that got titrated in, that it's starting to have the droplets turn pink, but of course it hasn't gotten to its equivalence point, but it's getting closer to that. But after 30 milliliters, our pH is now at 5.1, and so we'll see what happens the closer we get to our equivalence point. Okay, so a little bit earlier we came across our equivalence point, which was at 35 milliliters, and its pH at that time was at 6.0. It was super close to it. After 30 seconds, it was still that light pink, even though I was still a little unsure, but now I am like 100% sure. And then after adding 2 milliliters, we've reached its end buffer point. It has gotten to this dark magenta pink color, and so this is the end of trial 2, and its ending pH at 37 milliliters was at 8.8, so it ended a lot differently than the last one did. So we'll see what happens in trial 3. Okay, so now we're on to trial 3, and its initial pH is 3.0 at 0 milliliters titrated. And so let's begin by adding 1 milliliter, and we'll check its pH and start this lab. Okay, so let's do this, and let's check its pH. So the pH after 1 milliliter has been added is 3.1. And so now we'll see as we continue this lab where this trial's equivalence point and endpoint are. Okay, so 10 milliliters into trial 3, and we have now a pH of 3.9, opposed to whenever we started, whenever the pH was at 3.0. So we'll see what happens the longer we go on to see what its equivalence point is going to be relatively around compared to the last 2 trials. Okay, so 20 milliliters titrated in. Our pH is now at a 4.5 as opposed to our initial being at 3.0, and whenever it was at 10 milliliters, it being a 3.9. So it's went up a few, and we'll see what happens the more milliliters we add. Okay, so we're 30 milliliters in to trial 3, and the pH has changed from what it previously was 4.5 to now 5. So we're getting pretty close, and around the 27 milliliter, whenever I was adding that, it started to have pink start to show. So we're getting pretty close to the equivalence point. So I'm going to be slowing down a little bit just to make sure that we get the right equivalence point so that we can understand the right endpoint and finish up this trial. Okay, so we're at 40 milliliters that has been titrated into our analyte, and the pH right now is at 6.2, and we're getting pretty close to an equivalence point. It still hasn't reached it lingering, but it is lingering longer than it just immediately dissipating to being completely colorless and clear. So we're getting close to it being at its equivalence point. So we'll see what happens after a few milliliters have been added. Okay, so checking back at the end of experiment 3, 41 milliliters was whenever it hit its equivalence point and it lingered for some time. I just wanted to check to make sure that it was. And then its end point was at, ironically, 41.5, where it turned into this darker pink. So at the 41 milliliter mark, the pH was at 7.0, while at 41.5, it jumped up to being at 8.7. So that's how we end trial 3 and then move on to our discussion analysis. So now we are on to our analysis of what just happened. So in here for our trials, our equivalence points were at, for trial 1, 40 milliliters. The moles of the titrant used was 0.02495, which you multiply your 1.4 grams divided by your molar mass of the KOH, which is 56.1, and that's where you get your moles. And moles of your analyte are the same because of your mole-to-mole ratio. Now, when looking for your analyte molarity, so for looking for your analyte molarity, you divide the moles by the amount of milliliters that you used. So ultimately for this analyte molarity of trial 1 was 6.62 times 10 to the negative 4th. And average molarity I'll go back to, but then our percent for our analyte is 72.7. And our percent error for these is 5% because of doing our thing. So going on to trial 2, 36 milliliters is the amount that was at an equivalence point. And then our moles for titrant and analyte are the same, 0.02495. And then our analyte molarity is we multiply that mole that we just stated by 36, and we get 6.931 times 10 to the negative 4th. And by using the 41 milliliters divided by 55 times 100, that's where we get our percent for analyte, which is 65.45%, and then our percent error is the same at 5%. Then with 41, our moles for our titrant analyte are the same, 0.02495, and then our average molarity, our analyte molarity is 6.085 times 10 to the negative 4th, and you get that by dividing your moles by your 41 milliliters that was stated earlier, and that's what you get. And then your percent analyte, I divided the 41 milliliters by the 55 milliliters of the total thing times 100, and you get 74.54%. And our percent error still remains the same at 5%. Then for our average is pretty easy. So what you do, so the answer to the average molarity in the 3 trials was 6.405 times 10 to the negative 4th. And I hope you have a wonderful rest of your time here.